Welcome to part 2 of our lesson on enhancing the extensibility of Java's Completable Futures framework. In this part of the lesson, we'll analyze case study EX5, which shows how to apply our Completable Future EX class we defined in part 1 of the lesson in order to reduce and multiply big fraction objects by using Java virtual threads in conjunction with Java Completable Futures. We'll also, of course, show how to use the more traditional Java common fork join pool in order to do the same processing. You can find this case study in the EX5 project in my Loom folder in my live lessons GitHub repository. We're now in the EX5 project in my IntelliJ IDE. Let's take a look at the EX5 class, which shows how to reduce and multiply big fraction objects concurrently using a subclass of the Java Completable Futures superclass. In particular, this example shows how to customize the Java Completable Futures framework to use arbitrary executor objects, including, but not limited to, the executor's new virtual thread per task executor that's provided in Java 19. In fact, you'll need to install Java 19 or beyond with Gradle version 7.6 or beyond and configure these together to run this example. So let's go ahead and take a look at the main entry point into the program. It starts by parsing the command line arguments, it then runs the tests, and then it prints the timing results from running the tests. Let's go ahead and take a look at how to run the tests. The tests start out by generating a random list of unreduced big fractions. And to do that, we use this generate random big fraction method. As you can see, this method goes ahead and uses the stream generate factor method to repeatedly call the make big fraction factor method. And make big fraction goes ahead and makes a very, very large numerator and a much smaller denominator, and then creates a big fraction out of that numerator and denominator pair. And we then limit the amount of processing of big fractions we create by using the limit method, giving it the count, and we take the results and we turn that stream into a list of random unreduced big fractions. We then use that list to call our helper method test fraction multiplications twice. The first time we're going to call it, we're going to use an instance of Completable Future EX that will spawn a virtual thread for each request to run asynchronously. The second time we run it, we're going to then set the executor of Completable Future EX to use the Java common fork join pool, which is the default of Completable Future. And then we go ahead and run test fraction multiplications again with the same list with a different execution executor. Let's go ahead and take a look at Completable Future EX. We looked at it briefly in the previous part of the lesson, but I want to explore it in a bit more detail here so you can see how it actually works in practice. So the basic idea of this class is we're going to extend Completable Future and then provide a means of having a custom executor. And we're going to use some of the virtual methods that were defined in Java 9 in order to carry out this customization of the Completable Futures framework. The first thing we do inside Completable Future EX is define a private static field called sexec, which will be initialized to the executor return from the executor's new virtual thread per task executor factory method. So that's the default. It'll spawn a new virtual thread for every request that's going to be run by the Completable Futures framework. Because that may not be the only way we want to do the processing, we define a mutator method called setExecutor that can be used to replace sexec with some arbitrary executor, such as a fixed size executor, or the common fork join executor, or a new cached executor, etc., etc., etc. We'll return the previous executor just so you can chain these things together if you'd like to. Now we go ahead and start customizing these hook methods that are defined by the Completable Futures framework a la Java 9. The first thing we do is we define the default executor method, which is a hook method that returns whatever the current value of the default executor is, which starts out spawning a virtual thread for each of the requests to be processed, but can be overridden as we've seen. Next, we go ahead and override the new incomplete future factory method, which plays the role of a virtual constructor that makes a new incomplete version of Completable Future, which in our case, of course, is Completable Future EX. And that's what will then be returned to these completion stage methods to do the processing in the right context. And then finally, we go ahead and implement the supply async method, which is basically another factor method. And this returns a new completable future EX that will be asynchronously completed by a task running as a virtual thread, by default, of course, with the value obtained by calling the given supplier. So it's virtual thread until we go ahead and change the executor. If you take a look at the implementation of supply async, it takes the supplier, it makes a new instance of completable future EX, which is this class, and then it goes ahead and it calls the complete async method, passing in the supplier. And complete async will then arrange to run that supplier in the appropriate executor context, which again by default will be running in a virtual thread for each of the requests that are passed to supply async. So now that we've got a better view of what the completable future EX class is going to do, let's go ahead and take a look at what the EX5 driver is going to use to drive this particular class. And to do that, we need to look at test fraction multiplications. So we pop down there, and you can see the first thing we do is we make ourselves a string buffer to keep track of the output if we want to use debugging. And then we go ahead and make ourselves a local variable, which is of type function, that takes a big fraction and returns a completable future to an updated version of that big fraction. And here's how it works. It will take an unreduced fraction, and then it'll then use the supply async factor method on the completable future EX class we just looked at to go ahead and reduce that big fraction, initially in its own virtual thread. When that processing is done, then the completable future returned by supply async will complete, and the completion stage method then apply async will be called. And that will turn around and multiply that reduced fraction by some big reduced fraction constant that we define here. It's just for kicks, this is what it looks like. It's just a very, very large, big fraction that's been reduced. And this processing will also take place asynchronously, and initially it'll take place in a virtual thread as well. So that's the reduce and multiply fraction function that we define. And this is just to make the rest of the code a little bit clearer. Let's take a look now at big fraction list. We turn that into a stream. That was that list of unreduced big fractions we generated earlier. Then we use the map stream method, which is an intermediate operation that will apply this mapper function, which, as you can see, will reduce and multiply each big fraction asynchronously. And what we get back here is a stream of completable futures to big fractions. We then go ahead and use the collect terminal operation to trigger all the intermediate operation processing, and it'll return a completable future to a list of big fraction objects that are in the midst of being reduced and multiplied asynchronously. And the way this works is we have a factor method called toFuture, which is defined on this class, which is the list of futures collector. And list of future collector is going to take a stream of completable futures, and it's going to store them into a list of completable futures, and then it will return a completable future to a list of the completable futures that have completed when all the processing is done running asynchronously. This is a very straightforward collector. We have a method called supplier that makes a new array list using the constructor reference syntax from Java 8. We then go ahead and make ourselves an accumulator, which will add each element in the stream to this list that we just created. We'll ignore the combiner because we're not using parallel streams. But the interesting method here is the finisher method. And you can see the finisher method is going to take that list of completable futures to objects of type T, and then go ahead and use the all of arbitrary arity method to wait for them all to complete. And it doesn't actually wait, it actually returns a completable future that, when complete, indicates that the processing is finished successfully, in which case we turn that list of completable futures into a stream, use the map intermediate operation to join all the completable futures to convert them into objects as opposed to completable futures to objects. This call will never block because we wouldn't have gotten here if all the asynchronous processing hadn't completed. And the last thing we do is we collect all the results into a list. So we get back a completable future to a list of completed objects. So if we pop back out to our driver program here, you can see that we get back a single completable future. When that finishes, that means everything's done being processed. We then call the then compose method, which is another completion stage method on completable future. And we sort and print the list that we got back. And sort and print list is also very clever. You can see what it does is it uses our completable future EX class to asynchronously and concurrently quicksort the list at the same time that we're asynchronously and concurrently heap sorting the list. We get back to completable futures here, and then we use the except either method, which is another completion stage method in completable future, which basically says whether quicksort finishes first or heap sort finishes first, I don't care. I just take the result that finished first and I go ahead and print the results. So that's essentially the way that the program works. Now, if you take a look at the driver, you can see we call it twice, once using the mechanism that defines virtual threads per request, which is the default executor, and then once using the common fork join pool in Java's fork join framework. So let's go ahead and run the program and we'll see what the results are. And of course, as always, your mileage may vary, so you should run this program in your environment with your hardware and your tests and so on. In this particular case, we're going to be running this with, I believe it's 100 big fractions that are generated randomly. So this can actually take a little while because that's a lot of processing to do. You can see that we define the count to be 100 and we turned off debugging by default. We could always change that if we wanted to. And let's see the results that we got here. So the results come back sorted from fastest to slowest. And you can see that the completable future implementation that used the common fork join pool was just a tiny bit faster than the one that used virtual threads. And that's not too surprising because of the way things work under the hood. There's a few extra layers of virtual threads you don't have with the common fork join pool by itself. In fact, virtual threads are implemented using a fork join pool of various flavors. But you can see the results are quite similar. So hopefully this example has shown you some interesting things about how you can customize the completable futures framework by overriding these hook methods and the factor methods to be able to customize the executor used to create the context in which supplier tasks are run asynchronously.